Hello everyone, it's very exciting to be here. I'm Stephen Zhang from AI and HPC department at Inspur. Today I'd like to share our latest work on the multi-level AI infrastructure for high-efficient training of jet-scale model. In recent years, a new successful paradigm for building AI systems has emerged. Train one model on a huge amount of data and adapt it to many applications. Since 2018, the internet giants and well-funded AI companies and institutes are bidding on the parameters at a feverish pace, both to drive higher performance and to flex their muscles, notably in the language models, so where the internet provides the mountains of unlabeled data for unsupervised and semi-supervised pre-training. So as shown in the left figure, the size of the language model has shown an exponential growth trend over the past 3 years, from the BERT that has 110 million parameters, the GPT-2 that has 1.5 billion parameters, and the Megatron LM, the Turing-NLG, and the GPT-3 that has 175 billion parameters. In 2021, an Inspur released with Yuan 1.0, a 245 billion parameters Chinese language model, consuming about 5,000 petaflops day computing power. And later, NVIDIA and Microsoft used DeepSpeed and Megatron to train the Megatron Turing-NLG with 530 billion parameters. This is the world's largest and most powerful generative language model. So according to Kaplan's point of view, the current NLP model is far from reaching the limit of model performance, and increasing the amount of model parameters and training data is still the most effective means to improve the model performance. The developers of large-scale jet-scale models must overcome 3 technical obstacles: the data, the computing power, and the enormous energy consumption. So first for the data, large models need lots of data, but large-scale sources like the web and the digital libraries can lack high-quality data. And for the computing power, traditional hardware architecture will struggle to process the jet-scale model, which demands a tremendous parallel computing on heterogeneous computing chips like CPU, GPU, and other acceleration cards. So third one is the energy consumption. Training such jet-scale networks burns a lot of kilowatts. A 2019 study found that using fossil fuel training a 200 million parameter transformer model on 8 NVIDIA P100 GPUs will emit nearly as much carbon dioxide as an average car over 5 years of driving. So just imagine how much energy demands for a trillion parameter level model training. As an industry leader in the AI computing, Inspur has been working on to explore the efficient training methods for large models from the underlying computing infrastructure to the upper layer algorithms. Yuan 1.0 is the largest Chinese language model with 245.7 billion parameters. That is much larger than the GPT-3. Most importantly, we achieve the highest GPU real performance, that is 140 teraflops per A100. That means we can take good advantage of the computing power of each GPU, use less GPU cards to train larger model. On the other hand, we also put forward a massive data filtering system to filter 866 terabyte text data from the internet, obtaining a 5 terabyte high-quality Chinese language dataset, which is far larger than other language datasets like GPT-3 and Penguin Alpha. So the high-quality dataset make Yuan 1.0 a more powerful language model with comprehensive language capacity. Also, Yuan 1.0 has remarkable accuracy performance, achieved number 1 on Glue zero-shot and few-shot learning benchmark. So to determine the optimal model architecture for the Chinese language understanding, we have considered 3 types of pre-trained model structures: the encoder-decoder for Google T5, the language model for OpenAI GPT-3, and the prefix language model. This is a transformer of encoder and decoder. In general, the encoder-decoder is better suited for the language generation tasks, while the language model and prefix language model are better for the natural language understanding tasks. Thus, we first selected the language model and the prefix language model, and then further compared their performance on different downstream tasks. And the results shows that the language model performed better on zero-shot and few-shot learning, while the prefix language model performed well in the fine-tuning. While the fine-tuning typically results in a greater accuracy on most tasks, it consumes a lot of computing resources. In addition, the large-scale models have evolved to not require the fine-tuning for specific tasks, as their better generalization capabilities and applicabilities. So ultimately, the language model is selected as the foundation architecture of Yuan 1.0, and the parameters of language model affect both the accuracy and the performance of large-scale distributed training, including the numbers of layers, the hidden size, the global bench size, the micro bench size, and etc. So based on the hardware architecture, the model parameter design is optimized to achieve higher single-card performance. However, this is only the first step. Training a large-scale language model also faces the data and computing power challenges. So as we all know, the big data is the basis for successfully building the giant-scale models, and the amount of data will determine the scale of the model and its final performance. So we take GP3 for example. The scientist from OpenAI has collected 45 terabytes of data from sources such as Common Core, the Web Text 2, Box 1, Box 2, and Wikipedia. Furthermore, the high quality and highly correlated data are very beneficial for the model training as well. So for the model with training parameters like Yuan 1.0, it is very difficult to obtain a large enough set of high-quality data. Therefore, Inspur has developed a massive data filtering system, also called MDFS, which mainly uses Spark for data cleaning and filtering, and then screens the high-quality corpus based on the BERT-like model. In addition, the whole process of MDFS needs to be conducted on a cluster of 36 high-performance servers. Specifically, the MDFF system consists of 3 steps: the data collection, coarse filtering, and fine filtering. First of all, in the data collection stage, 846 terabytes of data is collected from the Common Core, the open source corpus, the Chinese boxes. Then, in the coarse filtering stage, using a series of data cleaning and screening methods to refine the dataset to 6 terabytes. And in the fine filtering stage, a BERT-based model is trained to classify and evaluate the text quality of this corpora, in order to just preserve the high-quality dataset of valuable and meaningful data, and removing the low-quality fragments. Finally, a 5 terabyte high-quality Chinese language dataset is obtained. So after getting the high-quality large enough dataset, we came across the biggest challenge. That is, how to realize high-efficient training of such a large model. As we all know, currently the GPU memory is up to around tens of gigabytes, and training a large model with 200 billion parameters demands up to a few terabytes of GPU memory, which obviously can be allocated on a single card or a single GPU server. So we need to distribute the huge computing power across thousands of GPUs. Also, the algorithms need to be specifically designed to solve the problem of GPU memory consumption and the utilization of GPU performance. So here we adopt the 3D parallel strategy, the tensor parallelism, pipeline parallelism, and the data parallelism, using more than 2,000 GPUs for training. Meanwhile, we also follow the principles like increasing the sequence length as much as possible, reducing the number of model layers and increasing the size of hidden layers. Finally, we complete the training of Yuan 1.0 on 2,128 GPUs in just 16 days overall, including 180 billion tokens and achieving 140 teraflops of single GPU computing performance. In contrast, the GPT-3, which employed 10,000 GPU cards, has a single GPU computing performance of only 12 teraflops. So, for more information on Yuan 1.0, please visit below link to get the whole paper, so where we demonstrate the details regarding the model design, the dataset generation, and the training strategy. As mentioned before, the training such a huge model will also trigger big challenges on the hardware architecture. For Yuan 1.0, the span leaf architecture is used to scale the cluster into hundreds of servers. Specifically, 266 of 8 A100 nodes are employed. So there are 2,128 A100 in total. And the tensor parallelism occurs in one node, in which each A100 GPU hosts one is of parameters on each layer of the transformer, and one group is formed by 38 A100 nodes, in which one complete Yuan 1.0 can be placed. And the pipeline parallelism occurs in one group, and each node hosts two layers. And the whole dataset will be distributed into 7 parts, so each of which is allocated in one group for data parallelism. In order to ensure the performance of the whole cluster, the multi-level test is required. And for the single node, we will perform different test cases to verify the key components, including the CPU, memory, the GPU, IB, NIC, and storage. So upon the basic components test, here are the connectivity verifications, including the GPU P2P bandwidth and the CPU to GPU bandwidth. Also, we have developed the test tools that can support various frameworks, including the TensorFlow, the PyTorch, and the benchmarks like MLPerf. So at the same time, the debug and the parameter optimization will be conducted to solve the problems and improve the single node performance in very short time. Because we have rich experience on the MLPerf benchmark testing and service for the global top customers. In addition, the networking test consists of a perf test to verify IB bandwidth and latency, and the perf test CUDA to verify the GDR bandwidth, and the NICO test to verify the multi-node GDR bandwidth. So if the single node and the networking tests are both passed, the multi-node test will be conducted eventually to observe the whole performance of the cluster. And Inspur has established the full stack test capacities and diverse automatic testing tools needed for building and fine-tuning of a large-scale GPU cluster, and with which we have helped many customers to gain the Gen-scale model training capacity. So when it comes to the Gen-scale model training, people often think that the cluster consists of a highest configuration server can accelerate the training speed. So the most typical case is to use 8 InfiniBands to improve the networking bandwidth and reduce the data communication time. Admittedly, the shorter the proportion of communication time, the higher the proportion of computing, and the higher the computing efficiency of the overall system. So increasing the network bandwidth can increase the peak bandwidth of communication, thereby reducing the communication time and communication proportion. So, but there is a marginal effect here. The conclusion taken as a whole may differ from just focusing on the performance. For example, for a 2 IB system, the communication proportion is 3.6%. So if add 2 more IB cards, the communication proportion will reduce to 1.8% accordingly. So while the performance will improve by 1.9%. So if continuously improve the IB cards to 8, the communication proportion will further reduce to 0.9%, while the performance will only have 0.9% gain compared to the 4IB system, and 2.8% gain versus the 2IB system. So based on the practice on Yuan 1.0 training, the 2IB cards can provide adequate bandwidth for a 200 billion level model training. So from the cost and the energy perspective, the results can be even more staggering. Here we compare the cluster that we built for Yuan 1.0, which uses 8 A100 2IB system, and the DGX A100 SuperPod that uses 8 A100 8 InfiniBand system. Just assuming both have the cluster both have 266 nodes of 8 A100 system, and the main difference is the quantity of the IB cards, so which will further lead to the different quantity of the leaf and spine switches. So as shown in the chart, the cluster power of Yuan 1.0 cluster is 1,600 kilowatts, while that of the DGX A100 SuperPod is more than 2,000 kilowatts. That means Yuan 1.0 cluster will save 16.5% energy one day. And moreover, we put forward this equation just to correlate the energy usage to train a large-scale model with the performance of a single card and the energy usage of the cluster per day. Obviously, if we want to use less energy to train the Zhang-scale model, we can just improve the single card performance through collaboration optimization of the hardware and software, just like what we do in Yuan 1.0 design, or reduce the energy usage of the cluster through employing the most appropriate hardware configuration. So as the parameters of pre-trained model is still increasing dramatically, we also propose a 2008 A100 super cluster for the future Zhang-scale model training. Actually, this has reached the limitation of 2-level spin leaf topology, and this system will be more powerful than that we use for Yuan 1.0. So as we have presented today, the Zhang-scale model training is a sophisticated system engineering, while including the model design, the system design, cluster design, and multi-level tests and optimizations. So Inspur has built full stack capacity to support Zhang-scale model development based on the practice of Yuan 1.0 and hundreds of successful use cases with internet giants and top AI research institute customers. And we are very glad to have deep discussions and collaborations with more friends from all over the world. So here, I'd like to also show the Inspur current AI products portfolio. So on the AI computing platform, we not only have the training servers, the inference servers, edge servers, but also we have the FPGA cards, the smart NIC, and the VPU cards. So on the resource platform, the AI Station Suite can help our customers to realize the high-efficient GPU resource management and one-stop AI model development and deployment. So on the algorithm platform, apart from Yuan 1.0, there are also the AutoML Suite, TF2, LMS, that for the different AI scenarios. And the whole portfolio has been supporting key AI workloads and applications of hundreds of customers around the world. So here is a detailed introduction of our current generation AI computing products. As you can see, we have the most complete portfolio in the industry that supports all kinds of AI workloads and empower multiple AI applications. And last but not the least, Inspur has achieved #1 revenue share of worldwide AI server sales in 2020 with 16.7%. And this number has improved to 20% in 2021. Also, we have won 22 out of 57 benchmark champions of MLPerf AI training and inference in the 2021, and we are committed to use the most advanced AI products and the full-stack AI capacities to help our customers empower their business with AI better and faster. Thank you.